Hello. So we are now going to start gravity currents, which are a little different from plumes that we recently studied. So plumes, if you remember, are primarily vertical flows, which flows in vertical direction because of the buoyancy, because of density difference between one fluid with the ambient fluid. Similarly, we have gravity currents, which are also driven by density difference. So these are also called density driven flows, but in this case flow happens primarily in horizontal direction. In some examples you can see here, for instance this one, you can see how this fluid, this we generally call it as dust storm, that is flowing in this direction, right, where we have the ambient fluid which is basically surrounding this dust storm. Likewise, you have another example where we have this fluid which is flowing on top of salty water, where this yellowish water has lighter density than the salt water in the sea, right? And this fluid might be coming from the river, or maybe from other sources. And this one is also moving here in horizontal direction. Okay, so this example show that even if buoyancy force is applied vertically upward or downward, this can create horizontal flows if there is some sort of horizontal boundary. So in this case, in first case for instance, you have this, let's assume this is rho naught and this is rho ambient. So rho naught is actually greater than rho ambient. Okay, and that's why there is this density driven flow happening, and we will quickly see how this density difference in vertical direction creates flow in the horizontal direction. Likewise, you have another set of example here, which is from a lab experiment. You have a plume, a gravity current, which is flowing in this direction, and this is the same gravity current, which you can see how it is propagating in time. So earlier, it is this image is from 2.3 second, 3.9 second, and it goes all the way up to 7 second. Okay, or maybe these are different units in time. It may be seconds, or it may even be in minute, which I'm not very sure, but this is from the same experiment, and it shows how gravity current is progressing in time. Okay, so the definition of gravity current can be read as: gravity currents are primarily horizontal flows driven due to density difference between fluids. Okay, so we saw these examples where we have two different type of fluids, where one fluid is heavier than the other fluid. And in this example, experimental example also, we have a similar situation where you can call this as rho naught, and this one as rho ambient, where rho ambient is smaller than rho naught here. Okay, so what exactly happening here? So let's assume this is the gravity current, where this is the impermeable boundary or solid boundary, and this is the gravity current of density rho naught, and outside density here is rho a, which is same here, and this gravity current is flowing in horizontal direction. So what exactly happens here is, if you consider 2 points, let's say this point 1 and this is point 2, and if you want to find now the pressure between point 1, pressure difference between point 1 and point 2, so we can first assume there is, let's say, a reference point where we can assume that pressure is PA. So P1 here would be PA, or if we define this PA to be exactly at the top of the gravity current, for instance, my apologies, we'll define this here, that will make it much easier to understand. So this will become, P1 will become PA plus rho naught GH. Let's consider this as H. In P2 will be PA plus rho A GH. So P1 minus P2 will simply be equal to rho naught minus rho a gh, right? So you can see how the pressure between point 0.1 and point 0.2 has a non-zero value. So pressure at point 0.1 is greater than pressure at point 0.2, and now because there is horizontal pressure gradient, flow actually happens in horizontal direction. It is very straightforward. We are simply using hydrostatic pressure condition here, and that tells us the pressure difference, and because of pressure difference there is horizontal flow. So this is the basic pressure difference that comes from density difference, and that drives the flow in such a case. Okay, so these are called gravity currents, and as you can see from these images, these are very it occurs quite frequently in nature, and that is why we want to understand how gravity current flows and what are important parameters while studying gravity current. Okay, so in this case, again, this is the same example where we assume this is the gravity current which is flowing in this direction, and let's assume this has a velocity u naught, and it may have a height of h naught and has a density of rho naught, where ambient density is rho a. So here these are few things that we are interested in. U is the gravity current velocity, h naught is the gravity current height, rho naught is the gravity current density, and rho a here is the ambient density, right? So basically this flow that is happening will be because of rho naught minus rho a, so that is basically delta rho. So uh, flow will be basically a function of delta rho, h naught, and u. So these three parameters will be affecting the flow one way or the other. Either two parameters will decide the third parameter, or other two parameters will decide the first parameter. Okay, so we are trying to find a relation between these three parameters, and we will see how gravity current velocity is decided based on the density difference, or based on the height, or how height is decided based on the velocity and density difference, etc. Okay, so these are the things we are trying to model, and to be able to solve this problem theoretically, or to be able to find an analytical solution, we will make some simple changes to the configuration, and then we will try to solve this problem. So we will start with a thing called change of frame. So at the moment we know that we are assuming this is a solid boundary here, and this is the gravity current which is moving in this direction with velocity u, and we are assuming that u is 0 for ambient. Okay, so this is the current situation where gravity current is moving with a constant velocity in a static ambient. Okay, so this basically constant velocity u for gravity current in ambient velocity u is 0, which actually means that ambient is static. Okay, so this is the condition we have, but now we want to do the change in frame. So from here we will go, we'll apply a change in frame, and we will assume we assume that gravity current is static and ambient is velocity u. Okay, so this is all about relative velocity. We are concerned about relative velocity, that is capital U. So when ambient is zero, gravity current is flowing with capital velocity U. And now we change the frame of reference and we assume that our gravity current is static and ambient is moving. So our reverse problem now looks something like this. So this is the bottom and this is the gravity current, and let's assume we also have an upper boundary which, and here we assume that that is the velocity u, that is the ambient velocity, and u naught, let's call the gravity current velocity as u naught, and u naught is 0, which is now the gravity current velocity, where u here is the ambient velocity. Okay, so this is the change of frame where we assume the gravity current has become static and ambient is moving, and everything else will work exactly the same way because we are just applying a relative velocity, and with a relative velocity the system will still behave in same way as it was behaving before. Okay, and here we will assume that ambient density is rho a, gravity current density is rho naught, and u naught is 0, and also we will assume that because now this uh, gravity current thickness is having 0 velocity, so let's assume this is h naught, that is the thickness of the gravity current, and we also have total thickness, that is capital H, okay, for the whole medium. And because some part of the whole medium is now occupied by the gravity current, the ambient fluid here will also have some velocity, and let's assume that is velocity ua. Okay, so we will quickly summarize what all things we have here. Capital H, the total vertical thickness, h naught is the gravity current thickness, u is the ambient velocity original, and ua is the ambient velocity disturbed, okay, for h minus h naught, whereas this one is the velocity for h. Okay, so when we consider the complete layer that is coming from here to here, that has a velocity of capital U, and when we consider the smaller thickness, that has the velocity of ua. Okay, and also rho naught is the gravity current density, and rho A is the ambient density. Okay, so this is what we have got so far with static gravity current and moving ambient. So now we will try to use few equations here, and let us start with, let me copy this system here. Okay, so this is the complete system we have, and here we are going to define few points for analysis. So let's consider this is point A, this is point B, this is point C, that is point D, and this is point E. Okay, and we will start by applying Bernoulli equation between 2 points. So here we will apply uh, A and we apply Bernoulli equation between points A and C. Okay, and we will try to see how the pressure condition and everything else are related to each other. So how do we write Bernoulli equation? It has three different terms: PA by rho g plus UA square by 2g plus ZA is equal to PC by rho g plus UC square by 2g plus ZC. Okay, and what is the density at point A? That is equal to rho A, and density at point C is rho naught. So here we know that velocity UC is 0, as we have assumed velocity of the gravity current to be 0, right? That is here. So we are assuming gravity current velocity is 0 at this point, and that actually tells us that UC is 0, that is the gravity current velocity, right? And that is why this term will become 0. And we also know that ZA is equal to ZC, as we can see from the figure drawn above. So that becomes equal to, they cancel each other. And one thing we can do, okay, and then UA is simply equal to U, that is ambient velocity, right? And one more thing is that we will consider C as the reference point for pressure, such that PC is equal to 0. Okay, so this is a reference point we are considering, and because in Bernoulli equation we define one datum or one reference point where pressure is 0, and we try to define pressure condition at every other point based on that particular pressure. And that is why if we define PC is equal to 0, so this particular term also becomes 0. Okay, in that case, what we get here is PA over rho AG is minus U square 2G. Okay, and this actually tells us PA is simply minus U square rho A by 2. Okay, so this is what we have for pressure at point A. So this equation we are going to use, we will need this. Let's call it equation A, that is needed for subsequent derivations. Okay, and now the second condition is hydrostatic pressure condition, which we are going to use. And here we want to define pressure at few points. So first let's define pressure at point E and point D and also at point B. So based on hydrostatic pressure condition, we can define PB as PA minus rho A GH, okay, where H is known, rho is the ambient density, and PA is pressure at point A. And we know that pressure at point A is this one, so that becomes minus rho A U square over 2 minus rho A GH. Okay, so that is pressure at point A, sorry, not point A, point B. Likewise, pressure at point E will be PC minus rho naught GH naught. Okay, so if we go up here, so that's pressure, that's point E, and if you want to find pressure at point E, that must be PC minus rho naught GH naught. Okay, so that is given here, and remember that PC is assumed to be 0 here, and that is why PE simply will be equal to minus rho naught G H naught. All right, in similar manner we can define PD, which has to be similar to, so PD will be equal to PE minus rho ambient G H minus H naught. Okay, in PE here is minus rho naught G H naught minus rho A G H minus H naught. Okay, so this is how we define pressure at point B, point E, and point D, and this is with an assumption of hydrostatic pressure condition. And again, we can consider hydrostatic pressure condition, especially if the gravity current thickness is not very much, and if the vertical flow is significantly small. Okay, and we are going to use these pressure conditions in subsequent derivations. Okay, so now having considered Bernoulli equation at two different points and derived pressure condition, we can apply mass balance between two sections. Between AB and CD. Okay, so if we go back here, because we are considering the vertical velocity to be significantly small, the mass balance, mass flux through section AB must be equal to mass flux through section CD. Okay, so whatever flux is coming from the left must be going to the right, and that is why we can say m dot through AB must be equal to m dot through CD. And how do we find mass flux through this particular section? So through AB, that will simply be velocity, density times velocity times area, right? So rho A times u times height. Okay, and we are doing it for per unit thickness, and this will be equal to rho naught u naught h naught plus rho a ua h minus h naught. Okay, and this equation per unit thickness in the third axis, and that is into the paper, or the third axis apart from x and z. And here we know that u naught is 0, that is the gravity current velocity, which we have already considered, and that is why this equation will convert into uh rho a ua h minus h naught, and that gives us an expression for ua, that should be u, yeah, so u h over h minus h naught. Okay, where rho a simply cancel out because they are the same, and this is the equation we get. This is the mass flux balance, and we will call it equation number 2 or B. Okay, so now we have derived mass flux balance. So next we are going to derive momentum flux balance and also energy flux balance.